Okay, the voice has not come yet, but can you see my screen?
Yeah, I think you're okay, Felix, and it seems the recording has started. We didn't get the voice today. So you're fine. Yeah, carry on.
Right, so this presentation comes to you courtesy Microsoft Teams from the attic of my house in Manchester. I'd much rather be in a real meeting where I would actually get something to eat, but hey. So what I'm going to try to talk about is a bit of the history of high-speed rail. I'll try to canter through that quite quickly, and then sort some of the thinking behind how you can optimize a high-speed rail system. As Joan has said, I'm Professor Emeritus of Railway Systems Engineering at Birmingham. My key interest is in complexity and complication, and I act as an occasional railway consultant. So I'm interested in systems thinking, railway traction systems and control, that's signaling, ergonomics, and people in systems. And what I want to talk to you about today is lean design of railway systems, particularly high-speed railways. So let's have a quick look at what that is. By the way, the person in the top left corner was present at the Rail Live about 3 years ago, and as you can see, he had full high-vi, at least in terms of the bow tie. So very high-speed railways I define as those which exceed 70 meters per second, so that's about 252 kilometers per hour. I'm going to talk a little bit about the history, as I said, the glory days of the railway, and then I'm going to talk about some of the optimization approaches to railways that we've come across during my career. As you can see on the graph, when we talk about very high-speed railways, the speed in operation is significantly different from what people can achieve in tests or when they try to make a point. So in general, most high-speed railways sort of aim for 360 kilometers per hour maximum in operation. But what does it do, this high speed? Well, the idea is that it shrinks a country. And what I'm showing here with circles, which lots of my students will know, or former students, is how far you can go in an hour if you go at a particular speed. And the sort of ochre circle, you get beyond Manchester in 1 hour from St. Paul's Cathedral. Well, actually, more likely from Euston. Now, people use that for all sorts of purposes. China uses it to create a nation, to build a nation. And you can see here the Chinese railway map for about 2020. And here is their plan for the high-speed railway network, which is expected to cover the whole of the country, because what's also obvious is that Beijing is not actually in the center of China. It's quite a bit in the northeast periphery. Okay, yes, you can still go to Harbin, which is further away, but it's really needed if you want to integrate a country the size of China. So it's a nation building project. So from about 1820s, railways were in the business of shrinking time and space, and it allowed you to have fresh food. It allowed you to work in different places. It allowed you to go on holiday because the amount of time available for holidays was limited. So getting to the holiday quickly was important, which is now today why lots of people always take planes to go on holiday, because it increases the holiday time rather than the travel. And of course, it allowed better work-life balances for commuters, and to some extent that has changed through the pandemic. But in terms of social health, I think it would be better if people did commute at least part of the time, but that's my personal view. So from 1820 to about 1950, the railways were speeding across Europe and the world, both for passengers and freight. And I do like a very old picture here, the steam locomotive Lyons, locomotion number 7. So it was built by Stephenson, and it was operating until about 1912. It wasn't going fast, but it could haul a whole train of wagons at 4 to 5 miles per hour. And that at the time was world leading speed and very, very efficient while it was running. So I think it's an important point that we see that even in the earliest days of railways, speed was important, even if it was limited. Stephenson then built the railway across Chat Moss, pretty much straight over a very long distance. It was effectively a high-speed railway in all but name. And even today, the railways are still running on this embankment at 110 miles per hour, which is an absolutely amazing achievement. Now, the Rainhill trials of the London, Liverpool and Manchester Railway, they were all about speed. Well, were they? No, actually, they were more about reliability, because the idea was that you had to achieve 48 kilometers per hour several times, and you had to work for a whole day safely and reliably. And on the third day, Rocket covered more than twice the distance between Liverpool and Manchester. And only Rocket actually was successful, which of course led to the huge success of Stephenson and his locomotive factory, and Robert Stephenson as well. And it's still around. What happened next in the high-speed stakes? To my mind, the most significant ones were the tests which were undertaken on the Zossen-Marienfelde military railway, where AEG and Siemens Halske had produced rail cars, just simple 4-axle vehicles, and were demonstrating that you could go at over 200 kilometers per hour. The peculiar overhead line arrangement would not have been suitable for a wider use, because points were rather a bit of a problem, but for a test they were amazing. It was 3-phase, of course, in order to minimize the difficulty of doing this job. The 3-phase supply was relatively low voltage, but it was already industrial frequency. And then, of course, it was all taken down. But very impressive to my mind, and they did a fair number of tests, and I think one of them actually was slightly faster than the other. In Britain, meanwhile, we were building steam locomotives, and the city of Truro was probably the first locomotive to be able to run at 100 miles per hour. The record is not clear. It could have been 97, 100 or 102. And of course, it needed 2.045 meter driving wheels in order to cope with the speed in the cylinders. The Deutsche Reichsbahn was also competing. They built the first locomotive, or rather one of the first locomotives, running at 200 kilometers per hour. An amazing achievement in many ways, but probably most impressive was the time between leaving the works and actually doing the trial run. 1935, and then in 1936 it was already running at high speed. So again, an amazing achievement. The driving wheels were even larger at 2.3 meters. And then we had Mallard, who managed just a little bit more than the German locomotive on 3rd of July 1938. And again, it was outshopped at the beginning of March of the same year. So within 4 months, it was actually achieving an absolutely amazing result. So, but it was very strange. We had electric locomotives, or rather electric trains, in 1906. And here were people building very, very high-speed steam locomotives in the UK. And that was basically the huge successes until the 1950s, when the railways were doing extremely well. They were going faster than any other means of transport, and they were reliable and reasonably cheap to run. But in the 1960s, the middle classes became wealthier, they became aspirational, they wanted more, and leading petrol allowed you to go faster and at greater speeds while keeping the engines in good nick. The cars were reliable, and the motorways avoided the conurbations, which meant you could achieve high speeds through a long distance. And by the 1970s, lots of countries built motorway networks. Convenience and flexibility have become the sort of watchword, and passenger and freight traffic started to avoid railways more and more because the other forms of transport were a bit more convenient. And then, of course, you could get a hell of a long way in 2 hours, like Nice, Toulouse and Bordeaux for the richer people in Britain for their holidays in the south of France. And another thing which was important and still is important, I think, is that lots of people enjoyed being in control when driving. So the railways had to act, and they did. And it all went back to the 1930s when Deutsche Reichsbahn had conducted some trials with 20 kV 50 Hertz on the Höllentalbahn. The French recognized the potential for the higher power levels available compared to 15 kV 16 Hertz and the French 1500 volts DC, Belgian 3000 volts. And they took on the challenge of using this system in France, and they managed to do quite a lot of very significant tests from about the 1950s. And by that stage, there were 200 km per hour electric trains. Japan did the same thing. They built the line from Tokyo to Osaka using standard gauge in order to avoid having slower trains, freight and suburban trains encroaching on the high-speed network. And of course, the first Shinkansen line opened for operation in 1964. In other places, things went a bit strange. So the Aero train ran in France, and I'll show a picture of that. But this is the picture of the 331 kilometer test in France. What you can see is a lot of dust coming up at the back, and that's basically the locomotive was hammering the track to bits. And we'll see that just now. The track had to be completely relaid after the tests. Well, the last test was the fastest, and so obviously the track infrastructure was a bit problematic. There was a second speed record in 1990 going at 550 kilometers per hour. That was largely a reaction to the Germans getting to above 400. And then, of course, the French did the very, very big record at 160 meters per second, or 574 kilometers per hour. An amazing achievement, and you can't see a dust cloud, unlike at the 515 kilometers per hour. That's because people were using granite for the ballast, and the trains were built in a much better way with much lower track forces. So an amazing achievement, nevertheless. Of course, I also have to show a couple of diesel trains, the HST and the Spanish high-speed train. The problem with diesel is that it's really, really difficult because you're carrying the prime mover with you. It's very difficult to achieve very high speeds, and also because you have to carry your fuel. So my overview here is of the development of high speeds, and as you can see from 1829 at the rocket, 50 kilometers per hour roughly, to the TGV Est test in 2007. So an amazing change, and you can see that it's really all about electrification to get the very high speeds. So I was saying that I was going to mention the Aero train, which to my mind was an early Hyperloop with probably the same potential success rate as Hyperloop, but that's just my prediction. I may be completely wrong. The actual track infrastructure is still in existence. The train, so to speak, was running on an air cushion, and it had a Caravelle type engine, which of course at the time was the noisiest jet engine you could possibly find. It was successful but it was all too expensive, particularly because you couldn't actually have trains of these. And then the German maglev system, which was a very successful experimental installation there's a facility at Shanghai International Airport, but basically it's again very heavy in terms of infrastructure and very difficult to justify economically. The Japanese seem to think that they have managed to justify their system economically, and they are building a line which will be running at 550 kilometers per hour, probably in about another 10 years. Again, slightly different and justifiable only because of the corridor in which it is being built. But let's go back to standard high-speed railways and why we need to optimize their design and operation. But high-speed rail needs to compete on time. That's very, very important. And what I've shown here is a graph which shows the cutover point where high-speed rail is fastest, but where it needs to be fastest because it's competing with air. And of course, conventional rail can't do that. And that's because the journey times just become too long. But we have now found that people are quite happy to actually travel 4 hours on a high-speed train over distances which are now 900,000 kilometers, even though the past history we always said, oh, it doesn't work, it's not possible. People don't want to go further than about something like 2 or 3 hours in total. There's other triggers as well. Some railways are running out of capacity. Some railways don't connect very well. So building high-speed rail can achieve that. And I've already mentioned Chinese high-speed railway, which is for capacity to some extent. It's certainly to combat air congestion, but it's largely about nation building. The Chinese high-speed rail network is full at Chinese New Year time, but otherwise it's not so overloaded at all. The Shinkansen system was definitely about capacity on road and rail and congestion. And the same for the Paris-Lyon TGV line, which basically took the air competition away because they just couldn't get the same times. Italy, similarly, the Germany, capacity and competition from the non-speed limited motorways, and the future Texas and California high-speed rail systems are really about capacity and competition from air and road and a cleaner mode of transport. Now I've got 2 examples of what I call good examples of high-speed rail, or in this case very high-speed rail. So South Korea is a very mountainous territory. There's severe weather situations, so it's difficult to do everything by car. There's a lot of air transport. So when I went to Korea in about 2002, I think it was, there were 8 747 planes flying from Seoul to Busan during the morning peak in 1 hour, which was for me absolutely mind-blowing. And Northern Korea, of course, has got very little. Let me just see whether I can get here the cursor. This is Pyongyang. This is the Chinese and Russian border up here. And you can see there's very little going on. Whereas here you've got Seoul, extremely densely populated over a large area. And down here, the industrial belt around Busan. So this is also sort of where I developed my theory that the high-speed network is best placed where the major conurbations are at least 300 kilometers apart. So if we look here, Seoul and Busan, Dongdaeju, Gwangju, Mokpo, they're all outside the 300 kilometers radius, which is, as I said, my sort of guess when it starts to be sensible. We look at the maps. On the left-hand side, you've got a map of the different cities, and on the right-hand side, you've got the high-speed rail network as it was in 2021. And you can see it really follows the population centers quite accurately. What's perhaps also interesting is that here in Seoul, there is now a second high-speed line, because this high-speed line is saturated into the center of Seoul, and commuting traffic from Daejeon, etc., is such that it was needed to create a parallel corridor. Also, it's got a different destination in the center. And if we look at the future plans, again, sorry, my 300-kilometer radius, of course, and the future plans for about 2030 roughly show that Korea is increasing the size of its high-speed network. So that's the double red lines. It's trying to reach all parts of the country, and perhaps most significantly, they are building an East Coast railway, which will go into North Korea, in the hope that this will all become a much better situation. And what's interesting is there are two cities within the 300 kilometers, and that's Incheon and Daejeon, and they're both large cities, and there is effectively high-speed rail commuting, which is why the need for the new section in the center. So again, 300 kilometers. The UK is rather different. So our high-speed rail network has got to deal with a different type of situation. I've used 300-kilometer radius, the same size as I had in Korea, and you can see that most of the large population centres are actually within the 300 kilometres from London. Of course, Sheffield and Leeds are outside, just about, I would say they're probably still inside. Newcastle is outside, Glasgow and Edinburgh. And that means that you probably don't need to go quite as fast as you need to go in countries like France, China, Korea, Spain, where the distances are bigger. There's also another problem in the UK in that we've got very densely populated areas. Land is expensive. The population is very articulate, which is my expression for saying no. And then, of course, land ownership is highly concentrated. The planning process is difficult, and there's a lack of belief in great things. So it's also a relatively small population. And the distribution is quite different from the way in which is distributed, for example, in Korea or in France. Anyway, we need to have origins and destinations. We need to have compatibility with existing networks. We need to reduce travel times by having shorter distance journeys, better acceleration and higher speed, the right station locations, etc. I'm now going to look at some of these issues here. So Japan uses a different approach to railway design, and that's why some of the tools which I'm going to talk about are sort of very specifically Japanese. In Europe, we identify the demand first, and then we look at lots of other things. In Japan, the first thing we do is we're looking at rolling stock, and we build the best rolling stock that money can pay, or money can get us, with lots of powered axles in order to accelerate very, very quickly. So this is a comparison between the Shinkansen and Pendolino, and we can see the most important feature is that a Shinkansen train is about 530 kilograms per seat, and the Pendolino about 960. And the Pendolino is hugely less powerful than a Shinkansen. So very, very different behaviors, and with the high acceleration braking rates, we can do lots of different things. So of course I had to have a picture of a a Japanese train. Now, you might think that Japanese would use the highest speed points that you can possibly get, points for 95 kilometers per hour, 230 kilometers per hour, as we will find on HS2 and already have on HS1. But the Japanese are actually quite modest. They often use 70 kilometer per hour points. Why do they do that? Because the land take becomes very, very much lower. What you have to do is brake very hard and accelerate very hard in order to keep capacity. And so this is a picture at the top, an approximate outline of the HS2 station at Birmingham interchange, and below a Shinkansen station, in this case Shin Yokohama, where your station is extremely short. The trains start braking significantly later, and they brake extremely hard, so their braking time is lower, and they disappear on a 70 kilometer per hour set of points into the station itself. So big advantage in terms of cost, big advantage in terms of maintenance and renewal, and of course a slightly greater problem in terms of managing the infrastructure safely. But Japan uses automatic braking, so that helps a lot. So I'm not going to go any further on this because I think I've sort of made my point. But I want to spend the next sort of 10-15 minutes looking at some of the tools which you can use to optimize high-speed railway. The sort of tools which I advocate are using generalized journey time in your design approach, the generalized cost of travel, continuous improvement, just-in-time production, value-adding and non-value-adding activities clearly defined, value streams, and something called the single-minute exchange of dies, and Taguchi process quality analysis. So what are the basics of travel behavior? Well, people travel for a purpose or to satisfy a need. That's quite obvious, really, which affects, of course, their willingness to pay for it, because if you haven't got much money, then you probably can't spend an awful lot, and it has to be a very important thing for which you're going to throw out a lot of money. It affects their choice of mode for the journey, and it affects their time of travel. So what we have seen in recent months, years, is the reduction in peak hour travel, which actually is a big benefit for the railway, because peak hour provision is expensive and the revenue has always been limited because of the capped rises of season tickets. And the time of travel is very important. Then, of course, you have factors which cover the whole of the journey as to whether you choose rail or not. The more difficult the journey, the less people will travel. But we have to, of course, define difficult, and I'll give an example of that. We can talk about the inconvenience in the weighting of journey parameters to make up the total, what I call the perceived journey time, because it's not just when you sit on a train. There's also the time when you earn the money for the journey, and there's the time when you actually go to the station, you wait for things, and that's the concept of the generalized journey time or journey cost. And that's summarized here on this slide. The generalized journey time takes into all these factors. So the actual time on the train or in a bus or car or whatever, the access time to the service, the waiting time before you can actually get on the train, then the time to get off the train, which is also contained in the access time. Something to do with the average delay, because that's a very big annoyance and the inconvenience factor. And therefore we usually weigh that at about 3. So if your delay is 5 minutes, you would perceive it as 15 minutes, and therefore that's what you put in. And then there's an inconvenience allowance on top of this, which depends on how many times you have to change. And it's all about the quality of the respective environment. If you have a comfortable train, then you will value your journey at 1 at maximum. If you have a super wonderful train and you can do other things during the journey, then you might feel the train journey is only taking half the time, which is certainly my view. And it all depends on why you are doing the journey. And of course, they're very personal factors. So you can't have a generalized journey time for everybody. You have to classify people to make it sensible. So here we've got an example of a project which is happening at the moment. You can see it's London Euston, and there's been very keen attention paid on ways in which you can cross the railway. That's not actually for access, but it's actually making sure that the railway does not cut the town in half as it does at present. And then you can see the sort of orangey lines which show the ways through HS2 station, because it's a long station. It's 400 meters plus, sort of probably more like 600 with the throat. And therefore you have to think very carefully how long it takes people to access this huge station. And I've just picked out another slide from the HS2, this consultation document. And what I find interesting is here is the station, the platforms are underneath here, and your underground stations are actually here and here. So wherever you are in the station, it takes you a bit of a walk to get to an underground station to get away, and the bus station will still be around here. I think cycle provision is probably absolutely tops on HS2 station in London, and I think I'm very much in favour of that. Now, the generalised cost function is a combination of the time it takes you to earn the fare. So that's the fare divided by A0, the value of time of the traveller, and the generalised journey time. So you end up with a cost in terms of minutes rather than a cost in terms of money. And I find that useful because the lifetime of all of us is limited to between 70 and 100 years. So the time is much more important in deciding what you want to do with your life than the cost. If you're rich, the time is worth, or rather a fare is worth a lot less for you, or it costs a lot less for you, etc. So because we'll see that in a slide a bit later on. So the value of time is important because it links the time and money based elements of the inconvenience of travel or transport. You can do the same type of generalized cost for a journey by car, by bus, by aeroplane, and you all use the same terminology, and it's actually quite interesting. The value of time can be estimated from average wages, and what you find is that a lot of people can't use the railway because it takes them far too long to actually save the money to pay for the fare, and that's becoming more and more obvious. And then of course you have to look at some of the ratings in terms of what people do on the train. So if I'm on a train, I usually work. So for me, the journey time is worth an enormous amount because I can use it all the time. If I stand on a London Underground train, then that's not the case. So my journey is wasted, or was wasted. Today, of course, most people use social media in every situation, so they don't actually realize how long the journeys and the waiting is. So if we do a value stream map, and that's one of these concepts which I quite like, this is a classical use of a railway. I've done it for a journey from London to Birmingham using HS2. You walk for 10 minutes from a bus station or whatever. You did tend to queue to buy a ticket. Of course, that's no longer going to be the case. You then have to walk to the gate, and on HS2 that can be quite a long time as you until you get to the end of the platform. You travel on your train, which is the time you actually want to spend. All the other times are non-value adding, so to speak, because you're not moving. And then you've got time to get out, and you've got time to go to your destination or a bus service or whatever. So the value added time or adding time is 60 minutes. The total time is 105. So the ratio is 57%. Now, if you show here the bits which people like, the walk is good for you. The queuing, the walking to the gate is not good for you, and getting out is also not good for you because you're probably in a big crowd. But it's lovely when you're actually on the train. Now, if we build HS2 to Birmingham, or when we build it, you'll be traveling for 50 minutes. That's an improvement. Now, what's the impact? Well, it's still the same things which you need to do outside it, which you're happy with or not. And the ratio of valuable time, usable time to the travel time is now actually lower. Well, it's quite obvious, but basically it's a very small proportion to some extent of the whole journey. Now, if you take out the time to get a ticket, then the picture looks a bit different. You're in the first slide without going at very high speed at 60 minutes. You've got a ratio of about 63%. You've still got the same sort of happiness or not happiness, but you no longer have to spend time getting the ticket. And if we reduce that, then of course the picture changes again, but the walking time probably becomes even more irritating because everything else is so short. And then you get your value adding time and the total time, and you improve a bit compared to the previous situation. So I've tried to transfer that into an example. Here are my values, and I've used £60 as the average ticket price, and so the full fare is about 60 on average, and I've assumed that people earn about £30 per 60 minutes, assuming social class A or B or a bit of C perhaps. So if we have an online ticket and have to collect it at the station, smartphone, then it takes us some time to do that. So we've got the situation with a ticket purchase, and that gives us a total time of 266 minutes. And that's what we would have to compare with traveling by plane or traveling by car or bus. I've not done that here. If we eliminate the ticket buying, and that means really eliminate it, we're not asking people to buy a ticket at home. We are really getting rid of the ticket process. Then we reduce that by 20 minutes. What you can see is that the actual journey time is relatively small compared to all the other things which go into your journey. So London Euston, there's a value stream map for what's happening when we get to London Euston. We arrive and we depart, and we have to alight and board. And we're only really the train, when the train is moving, it makes money. When it doesn't move, it doesn't make any money. So if we look at that as a set of trains, so a train going backwards and forwards between Birmingham and London, then the amount of value adding time is relatively small compared to the total time, because of course there's lots of things happening at the turnaround, which is the blue lines underneath. So the journey is going quite fast, as it should do. Now, if we put together several trains, So at that point, you have got 3 non-value adding activities at the same time. It's basically sitting in the station waiting to go out again. And that means you need a certain number of platforms to achieve that. Now, there's something called the single minute exchange of dies in manufacturing. And so if you remove the old die and heat the new die in place, in situ, then it takes a certain amount of time where the press can't do anything. And that's what we call internal activities, because they're in the process. Now, if we take the heating of the new die out of the process by doing it separately and lifting in a hot die, then we can actually externalize that time, and our total time for the setup becomes significantly shorter. That's what's being done in industry, and we can apply that to the railway. So we have got arrival, alighting, we've got boarding and departure, we've got a handover, toilet cleaning, wiping tables, collecting rubbish, and then we have to check the train as well. So that's using all of these activities by people going on the train. And that's what it looks like on the Tokaido train system. You have got here 2 crews who are going to clean 2 trains on the platforms. It's about a large number, as you can see. Now, if you take the collecting of rubbish out of that and do it on the train while it moves, you're externalizing it. And so here we've got internal activities again and external ones. And this is the lady who does it. It's an older picture, but I think it's clear. That's what she's collected on the way down into London. And it's in a very, very efficient use of time, because basically you can reduce your station dwell from an original time, you go to a reduced time by doing a lean operation by externalizing a certain activity. So we've now only got 2 non-value adding activities at the same time, and we only need 3 platforms, which saves us space, it saves us time, it saves us people. Now, what do we do with that? Well, one thing we could do with it is by looking at reducing our speed, because we don't need to reach the terminus so quickly if we have got less time at the turnaround. And that's interesting. What we can see here is different rates, different speed, maximum speeds for a run from London to Birmingham. And there are speed limits. And you can see that in some places there's no point actually having a train capable of going at 360 kilometers per hour. Something lower would probably do. And if we look at that in terms of the energy cost of going fast, here we've got speed increase. The red line is the energy consumption. The blue line is the journey time. And if we say, okay, we're normally going to go at 330 kilometers per hour, what happens if we go at 300 instead? Then what we see is a increase in journey time of 3 minutes. We can probably afford that because we have reduced our dwell time, or rather our turnaround time, and we can see an energy loss reduction of nearly 12%. So that sort of decision is very, very important in terms of reducing the cost of your system and optimizing the use of the infrastructure. Because remember, if you go a little bit faster then or less fast, then that has an influence on the capacity of the railway. Going slower reduces the braking distance and therefore the distance between trains. So if you do both things together, then here we've got a reduction in turnaround time, and we have got a reduction in the terminus occupation, etc. And I think that's where I'll probably stop. I've got some more slides to talk about Euston Station, but it's probably not time to do that because I want to give some time for questions. Finally, the staff requirement in Japan is probably very significantly higher than the requirement on a Avanti-West Coast train. I've simulated here a long class 390 and a Japanese train, and 44 instead of 11 people working is an amazing improvement. And that's all because of externalizing some of the activities. So thank you very much, Joan, and I shall stop at this point.
Perfect, Felix, thank you.
And I'm sorry I overran.
No, you're okay, you're all right. I don't know what's happened to the volume now. Something's gone not quite right. I think I'm okay now. Right. So I can't see any questions in the chat, but if anyone would like to raise their hand to ask Felix a question, they'd be more than welcome to do that. Or just unmute yourself and speak out. You covered a lot in that presentation, Felix, from the history all the way through.
Mistake.
No, it's very interesting. There we've got a question now coming in from Steve. Go on ahead, Steve.
Thank you, Steve.
Hi, Felix. Felix, just a question looking at the HS2 on its final journey up to Leeds and moving it from a sort of greenfield high-speed railway onto a expanded conventional railway. Just the lessons that we've learned so far from HS2. Just your thoughts on if it is about capacity rather than about absolute speed. Are we better building in existing railway corridors, which may be easier because there's less NIMBYs than trying to go across farmers' fields?
Well, I think the big problem is actually building new railways, or rather upgrading existing railways. To build a new railway next to an existing one, as is the MOT's proposal for the Nottingham, Newark, Leeds approach. I think that's a powerful way of doing things because you don't increase your corridors. Going through Nottingham is an attractive solution to my mind because it improves the access time hugely and therefore takes that bit out of the generalized cost. So I think there's lots of benefits of using existing facilities where you can, but you have to make very sure that you don't interrupt the existing traffic while you're doing it. Does that make sense?
Yeah, it does. I live very close to the Chiltern line and use it a lot, and it obviously runs now as a 2-track railway, but obviously used to be a 4-track at some point in the past. And I often ask myself the question, would we have been quicker and cheaper to have taken the Chiltern back to being a 4-track than actually building high speed 2? Now that wasn't the case when we thought high speed 2 was going to cost under 50 billion, but now it's going to look like sort of north of double that. Whether if we wound the clock back, 4-tracking the Chilterns might have been a viable option.
I think we can't wind the clock back. Expanding the Chiltern line back to 4-track would have been extremely disruptive, I think. And there may still be the case for adding a track to the Chiltern line, but purely for other things. I think it's more sensible to try and build something close to an existing railway, but as a new railway.
Okay, got it. Thank you very much.
What I regret is, the thing I really regret is that HS2 doesn't have a station in the Chilterns, because using very fast acceleration and very fast braking, you could afford a station there, and that would have made people in the Chilterns much happier about having a new railway on their doorstep.
Yeah, agreed. Thank you.
Thank you. Thanks, Steve. Anyone else putting their hand up or would like to ask a question? Yeah, I've got someone else there's got their hand up. Rory, would you like to unmute yourself, please, and ask your question? Thank you.
Hello. Yes, I suppose it's just a question that popped into my mind because it's slightly topical. A few weeks ago, the Golborne link got cancelled I think you're roughly from that area, Felix. So I just wondered what you thought about the axing of the Goulburn link, and if you had any thoughts on. I think there was our chairman at Network Rail, who said one of his reservations of the Goulburn link was it didn't solve all the problems that it was trying to solve. I don't know if you can shed light on what you think that might mean, or what you think about the Goulburn link being cancelled in general.
I think it means partly land take, it means cost. I think the best is always the enemy of the better in sort of a slight change to the saying, and to achieve the best is often impossible. And I think that was what was happening about the Goulburn link. It was a perfectly viable solution, but it wasn't covering, it didn't do everything. Now, I think in order to actually achieve a decent solution, it will be necessary to 4-track in the Behaviour junction area, which is where the big bottleneck is, so that you can actually get out of Crewe and travel without interruption north. So I can see that as a potential solution, but it's not going to be cheap. But maybe instead of costing 5 billion, it may cost 1 or 2 billion. But it's a pity to drop something which has been worked out.
All right, thank you.
Thank you, Felix. So we've probably got time for one more question if anyone else would like to ask a question. This is your opportunity. Yes, we've got another hand up there. Simon, go on ahead.
Yeah, thanks very much for the presentation. Just one question. Fast acceleration and hard braking doesn't sound very efficient. And also, do you think there's going to be some effect from decarbonisation on high-speed rail?
I mean, regardless of where you get your energy from, there is carbon involved either in the production or also in the construction of the system. So in that sense, decarbonisation, the best thing you can do is to reduce your top speed, which is what I was trying to illustrate to some extent. If you can achieve with a slightly lower top speed what you want to achieve, then that's the easiest way of saving energy and therefore carbon. Now, the thing about braking hard and accelerating hard on the continent, in Britain and in China, basically is not viable because your traction motors are not big enough. So the big difference in Japan is that they're using very big traction motors which can regenerate up to much higher speeds. And I do have to give this example. When I went to see the research center of central Japan, they had 3 traction motors on display, a small one, a medium-sized and a large one. And when I looked at the dates for these, it didn't make sense because the biggest one was the newest one. So in a meeting, I asked whether the labels had been put in the wrong place. And they said, no. The big traction motor allows us to recover energy up to line speed. And we don't do virtually any mechanical braking. And the Japanese are also working at methods of low speed braking, which are virtually all electrical. So there are big benefits of going fast and braking hard and accelerating hard, but you have to have the right type of train.
Very interesting. Thank you, Felix. Okay, I hope that answers your question, Simon. I think we're going to bring the presentation to a close now. So I'd just like to, on behalf of the PWI, thank Felix very much indeed for his time. Very interesting presentation, covered a lot of ground there. And thank you to everyone for joining and participating. Thank you. And we'll be running another Lunch and Learn. It's either next week or the following Tuesday. Sorry, I can't quite remember. But thanks everyone and enjoy the rest of your day. Thank you. Thanks.